most of the talk till now have been mostly industry related. And when I was invited to give a talk, I am an academician from IIT. I am a polymer technologist, having done my master's and PhD in polymer science from IIT Delhi. But currently I am working with the Textile, Polymer and Fiber Group. And my research interests are in nanotechnology applications in polymers and textiles. And my talk is going to be very different because I'm going to give you a glimpse of what this futuristic technology can give us. So most of it you may feel is at the research stage, but time is not far when these technologies will be commercialized in near future. Some work has already started, but I think more work will start in the near future. So the title of my talk is Nanotechnology, a New Route to Functional Polymers. So first of all, I would like to define what is nanoscience. So the word nano, as you know, it means 10 raised to the power minus 9. It's a Greek lingo for the word dwarf. So a nanometer is 1 billionth of a meter, and one definition of nanoscience concerns itself with the study of objects which are anywhere from 1 to 100 nanometer in size. As you can see here, the scale, the ant is at 1 meter, our some amino acid microbes are at 1 micron, and our 1 nanometer are some nanomaterial cage-like structure called POS. So there is a difference between nanoscience and nanotechnology. Science is more about understanding the theory, and technology is when you actually produce devices and products which are at nanoscale. So nanotechnology is the creation of functional materials, devices and systems through the understanding and control of matter at dimensions at nanoscale level, which is about, the classical definition is about 1 to 100 nanometers, where new functionalities and properties of matter are observed for increased broad range of application. So this is the definition of nanoscience and nanotechnology. So, this is just to give you a glimpse of, when I say nano, 10 raised to the power minus 9 of a meter, 1 billionth of a meter, then if you see the earth and you see a football and you see a nanomaterial. So our earth is about 12,000 plus kilometers and our football is about 22 centimeters. So this football is about 10 million times smaller than the earth, and our nanomaterial, which is a C60, 60 atoms of carbon into a cage structure, fullerene molecule, its diameter is 0.7 nanometer. So if you see, then you know the football, but our fullerene molecule, which almost looks like a football, and dimension in the nano range is 1 billion times smaller. So you can imagine the length scale we are talking at nano. So if you look at the introduction to nanomaterials, then they exhibit significantly. What is the interest in going to nano level? Because properties of material, physical, optical, electronic, all these properties change compared to their bulk counterparts. Nano silver behaves differently than silver. Nano copper behaves differently than copper. So when going to nanoscale, the properties, inherent properties of the material change. And this is because of the large surface to volume ratio and innovative applications in multitude of industries including electronics, medical, energy and polymer science. This is again a scale which you can see. The pointer is not working. So the scale you can see from 100 mm to 1 mm. So this is the mice at 100 mm, marble at 10 mm, tip of a pencil at 1000 microns, width of a human hair is about 50 to 100 microns, a red blood cell is in 10 microns, bacteria are in few microns, SARS-CoV virus was about 100 nanometer, antibodies are in the range of 10 nanometers, and a tryptophan molecule is 1 nanometer. So this is the scale from millimeter to nanometer scale, and the entities we are lying, which are lying in that range. So, there are a lot of nanofillers over a period of time which have been developed. So, they can be organic. So, organic will be from organic sources like natural fibers. The inorganic nanomaterials are basically made of metal or metal oxides like zinc oxide, silver nanoparticles or gold nanoparticles. Then they can be carbon based, so carbon nanotubes, carbon black and graphene, and clay and other based, so quantum dots, kyanite and bentonite. On the nanomaterials is where at least one of the dimensions in nano range. So when all the three dimensions are in nano range, it has these examples 0D. So the example is copper, gold and silver nanoparticles and quantum dots. Where one dimension is in nano is CNTs, nanowires and nanofibers. Where two dimensions are in nano is graphene oxide, boron nitride and black phosphorus. And then all the three dimensions are in nano are zeolite fluorus and metal oxide framework. So these are the layered structural materials which we have worked at IIT in our research. So we have worked on silicate clays where the clays are stacked structures of silica and oxygen. So silicate layers are stacked structures and the thickness of each silicate layer is 1 nanometer. The later dimensions can be more than 1 nanometer. So we have worked a lot with silicate layers. We have worked with carbon nanotubes, carbon nanofibers. We have worked with different kinds of silica particles of silica, and also POS molecule, which is a hybrid of the inner core structure is made up of silicon and oxygen, and outer is organic moieties which make it compatible with the polymer in which you are going to put it. So now one of the major areas in which nanomaterials are going are into polymer nanocomposites. Composites is conventional composites we all know. Fiber reinforced composites, glass fiber reinforced composites, carbon fiber reinforced composites. We all know, and they are very well established and they are in use. But polymer nanocomposites is where we are reinforcing the polymers with nanostructured materials, and not only nanostructured materials, but they are also dispersed at nano level in the or molecular level in the polymer, and nanofillers is where at least one of the dimensions is in nano range. So if you look at the nano versus micro composites, then you see the diagram here that stress versus strain diagram. For a polymer is the black line, for the traditional materials is the red line, and a nano composite would be the blue line. So it would retain its strength, and also at the same time it will retain the strain to break. So these are tougher materials. The key significant highlights of polymer nanocomposites are high surface area to aspect ratio of nanofillers which you are putting into the polymer. So it leads to, because in composites, as you know, the interface between the reinforcing material and the polymer is very important, because it is actually the place where the stress transfer takes place. So in nanomaterials, when you put The dispersion is at nano level, so there is a high interaction zone and volume between polymer and filler. Interfacial interactions rather than the bulk properties become more important, and improvement in properties are occurring at a much lower scale. So improvement in strength and modulus by elongation is maintained, as you can see in this picture. So this is a comparative slide of nano versus conventional composites. On this figure you can see on the y-axis is modulus over modulus of the matrix, and on the x-axis is the weight percent of the filler. So there are two graphs, one is for glass fiber reinforced composites and another is for nano composites. So if you want to increase the modulus, say by a factor of 2, then in glass fibers you may have to add 28% of the glass filler, but in nano composites you may just have to add 5-20% of the glass filler because of the high interaction volume. So that is the advantage. If your properties are increased at low volume fraction of the fillers, then the density increases are not there because glass fiber is heavy as compared to polymer. Plus, processing problems are not there. So many issues are there. So polymer nanocomposites have a lot of advantages over conventional composites, and this is because significant weight advantage, easier processing and better finishing, and this is all because of the difference in aspect ratios. So glass fibers, the aspect ratio N by D is only 20, whereas for nanoplates, if you are putting it is 100 to 500. So aspect ratio of nanomaterials is much higher than the conventional fillers. And the major problem is, because most of the nanomaterials are inorganic in nature. So when you try to mix them with the polymers are hydrophobic in nature, and most of the polymers are hydrophobic in nature and the nanofillers are hydrophilic in nature. So mixing them is a problem because of the incompatibility issues. And as you can see in this diagram, the below black is polymers and above is ceramics. And y-axis is use temperature and this is toughness. So you see polymers, the use temperature is low, so they are easy to process, but their toughness is low. But if you look at ceramics on the other hand, their use temperature is very high, but their toughness is low. So by mixing inorganic ceramic nanoparticles into the polymer can bridge the gap between the polymers and the ceramics. And this inspiration of nanocomposite is nothing new, but it has come from nature. Our own bone and teeth are examples of bio-nanocomposites. So a compact bone is dense deposit of minerals, chiefly calcium phosphate, and these calcium phosphate is the reinforcing filler, and collagen, the protein, is the matrix. These are arranged in concentric circles around a central haversial canal through which the blood and the lymph vessels flow. Our tooth is composed of two hard tissues, enamel and dentin, and enamel is also densely packed with calcium crystals of different orientations and collagen as the organic matrix. So our bone and teeth are examples of bio-nanocomposites. So they have been existing in nature, so nanocomposites is an inspiration from nature. Another example of a natural nanocomposite existing in nature is, if you have been to the seashore, you see these seashells. These seashells are so tough, they cannot break easily. Why? Because somebody has studied its structure and they found that argonite kind of an inorganic material in the form of nano bricks is arranged in a regular fashion into a matrix of a stretchy gummy protein. So it's again a combination of hard ceramic materials put into a matrix of gummy, soft protein, stretchy protein. And that combination gives you such a good toughness of the material. So, after this little bit of introduction on nanoscience and nanotechnology and nanocomposites, the first nanocomposite was used by Toyota Central Research Labs in Japan, which teamed up with Ube Industries, a Japanese resin supplier, in 1985, and they put this nylon 6 nano composite into the cars equipped with nano clay composites. And why did they use it? Because nylon 6 clay system, just by addition of the 5% of the nano clay, they could increase the tensile strength by 40%, modulus by 68%, flexural strength by 60%, flexural modulus by 126%, heat distortion temperature from 65 to 152. And in other polymer clay systems, solvent resistance, flame retardancy, thermal expansion, gas permeability. So actually this work was kind of work which attracted the world toward polymer nanocomposites when Toyota Research Lab used it in a car and demonstrated the use of nylon 6 clay system. And after that, there has been no looking back. In last 20-25 years, the research on polymer nanocomposites is exponentially increasing. And very soon they will be commercially very successful. You know. So polymer nanocomposite applications are into structural materials like automotive parts and civil construction, gas barriers for fuel tanks and packaging, biomaterials, coatings for aircraft, exteriors and technical textiles, and the market potential is continuously increasing. So, functional polymers, role of nanomaterials. So, integration of nanotechnology into polymer science has expanded the possibilities for creating advanced functions through structural control. Through structural control at the molecular scale. Functional polymer macromolecules specifically designed to possess unique properties, and these properties can range from physical and chemical attributes to biological functionalities, and it allows for the design of polymers that can respond to external stimuli. So smart polymers possess enhanced mechanical, electrical and optical properties. And the applications can be in tissue engineering, water treatment, drug delivery, energy applications, textile, smart materials, food packaging, and so on. So other organic nanomaterials are those which are synthesized from organic compounds including polymers, like these are lipids, peptides and nucleic acids, and these are basically micelles, liposome and nanogel, dendrimer, ferritin. So these are basically made up for biological materials, and they can be synthesized using various techniques, like dendrimers have been used for drug delivery and imaging. And this is nanocellulose. Cellulose, as you know, is one of the most abundant polymer on earth. So, you know, they are in the form of all the trees, all our vegetation, everything made up of cellulose. And this cellulose, you can do a special technology and bring it down to nanocellulose levels. And these nanocellulose levels are also gaining a lot of importance these days in the form of, you know, these are the 10 micrographs of the nanocellulose, and they can be used, they can be incorporated into polymers to improve, you know, increase the barrier properties of the polymers. And these can go into food packaging, and bacterial cellulose can go into biomedicine and water filtration experiment. So these are inorganic nanomaterials: silver, copper, gold, aluminium, zinc, lead, ceramic, silica, copper oxide, iron oxide. All these materials, another issue with this, that even if you synthesize metal and metal oxide nanoparticles, putting them into the polymer will not be easy because of incompatibility. So you have to functionalize these nanomaterials first, so that there is interaction between the nanomaterials and the polymer and a good composite is formed and the properties are transferred effectively. So carbon nanotubes is one of the supposed to be the most wonder material, one of the most important discoveries of nanoscience, and by S. Tijima. It was discovered in an accidental setup. So what are carbon nanotubes? These tube-shaped material made up of all carbon having diameter measuring at the nanoscale, and nanometer is 1 billionth of a meter or 10,000 times smaller than a millionaire, and CNTs are unique because of the bonding between the atoms. So these are carbon-carbon, all carbon-carbon bonds sheet, a graphite sheet rolled into a nanotube. So these can be single-walled and multi-walled. And carbon nanotubes theoretically have been found to be one of the highest tensile strength and modulus. And these are other properties. Carbon nanotubes exhibit various characteristic properties such as high elasticity, high thermal conductivity, high electrical conductivity, low density, and they are chemically also inert. And due to these interesting properties, carbon nanotubes have played a significant role in the field of nanotechnology, electronics, and other fields of material science. And they are also being looked into drug delivery, sensing, and water treatment. So there are different forms of carbon now: graphene, fullerene molecule, single-walled carbon nanotube, nanodiamonds, graphene oxide, and multi-walled carbon nanotubes. So these are different allotropes of carbon nanotubes which are now being worked into, and they have different properties. So one of the applications of carbon nanotubes, this is how the carbon nanotubes they are functionalized with bioactive molecules, and then they carry the active drug, and they can be incorporated into biological cells, and they can be made into sensors, and they are now being used to treat diseases like AIDS, tumor, osteopathy, and viral infection. And applications of carbon nanotubes are very many: biosensors, water treatment, cancer treatment, conducting polymer composites, antimicrobial activity, and biomaterials. So this is one example where polypropylene, PPCP, CNT, nanocomposite has been prepared by melt mixing. So you take the mixture of PPCP and CNT, and then you put it into the twin screw extruder for melt mixing, and then you take it to a micro injection molding machine for making the samples and then test it. And this is how it looks like under the microscope. And this kind of material can go into aerospace, sports equipment, sensors, EMI shielding, energy harvesting, and biomedical. A lot of research is being done in this area. And these are polymeric nanoparticles made up of polymers like PLGA, PEG, PVA, carboxymethyl cellulose. And the progress in biological therapies or immunotherapies has been promoted by advances of nanotechnology. Because they are in the nano range, the drug is incorporated, they can be injected into the body, and they can be easily biologically available for the body. And this is another example of polyurethane nanocomposite using nanocellulose fibers. So you can see the nanocellulose fibers, it has been put, and this is used as a hard wall. PU with nanocellulose fiber is being used as an implant for a hard wall. And improved thermal properties also. So this is wearables, electronic, skin, and here PDMS, polydimethyl thiioxide, silver flake, serpentine electrode structures have been made, and heat storing sodium acetate based hydrogel serves as an interfacial layer between the wearable device and the skin. So, role of nanomaterials in functional textiles, I will say. So, there is a lot of interest in textile also. It can give properties like water repellence, anti-static properties, wrinkle resistance, strength UV protection, computing, antibacterial and odor control, and sensors and optical displays. So these are the list of nanoparticles which is given here in the table, and they can go into different applications. I will not go through the table. So this information will be there on my slide. What are the different nanoparticles like zinc oxide and titanium dioxide nanoparticles can go into UV protection, fiber protection and oxidative catalysis. Like silver nanoparticles go for antibacterial finishing. Okay, so like this, so many types of different nanoparticles have been used in textiles. Water repellent textiles, as you can see, the water droplets fall, and this is just because of the roughness which has been created on the textile material. This is also known as the lotus leaf effect, where you see that on the lotus leaf, the water drops and it doesn't wet the leaf, and the water just falls and forms a dew drops. And they just, if you tilt the fiber, the leaf, it tilts and the water drop rolls out and takes it away with the If we can produce the same effect on our walls or our textiles, then these are known as super hydrophobic self-healing surfaces, and we are trying to get that effect on textiles as well as other materials by creating nanoscale roughness and then impregnating it with the nano materials. So these are silver silver nanoparticles which have been synthesized, and this has been used for antibacterial finishing. This is for smart textiles. This is little higher end. Here we also use PDMS and silver and zinc oxide nanorods, and you can get the supercapacitors from the self-healing yarn. So these are smart textiles, and these can be integrated into the textile materials, and it can sense the body functions also. And it can also, suppose a sensor is put here, then the sensor should not break. So the sensor is made in such a way that it is flexible here, or it is self-healing. Even if the circuit breaks, then it self-heals. So this kind of work is being done. So this is again in the smart textiles. So nanofibers is another important area where fibers which you can't see with the naked eye, you can only see under the microscope. A special technique called electrospinning is used to make these nanofibers, and nanofibers mimic the nanofibers inside the body, our muscles and tissues. So a lot of work in tissue engineering is being done on nanofibers. Okay, and this is a microscopy picture. So this scale you can see is about 8 microns. So you can see how beautiful. Now these fibers look, but they can't be seen. They can't be seen. They can be seen only under a scanning electron microscope. So these can be used for filtration, viruses and air filtration, etc., and even for gas sensing. Nanofibers can also be used into drug delivery. For example, this is the electrospinning machine where nanofiber is being made. So these are the chemotherapeutic drug and stimuli sensitive nanofiber. Now this is put into the rat which has got a cancer. So treatment of tumor during mice, and then there can be 2 ways in which the drug can be released. Either the pH change, heard of class properties. It makes it possible to precisely manipulate and control matter at the atomic and molecular scale, which makes it to design polymers which is previously unachievable, and customize chemical, physical and biological properties. And the impact of nanotechnology and functional polymers is extensive and still growing, maybe at the research stage, from improving the... I read somewhere, the future, what are the, some notable developments which are going to come up are spraying nanofibers for wound treatment, nanoparticle based drug delivery, as I said, nanomedicine, aerogel technology, and nanoparticle reinforced biopolymer films. So these are going to be the technologies which are going to really go up in the next coming future. And so thank you, and this is our IIT picture. And if you have any questions, I will be ready to take them, or we can discuss in the lunch time.